Okay, thank you. I'm currently a PhD student at ESO, so I will be talking about the work that I've been doing over the last 2 years. And the first question about direct imaging in the mid-infrared is, of course, why the mid-infrared? And to help illuminate that a bit, I've made a sketch here of the spectral energy distributions of a planet and a star. And you can already see that at 10 micron, the contrast between the two is a lot better than at around 1 micron. Additionally, there's a couple of molecules, such as methane and ammonia, that have absorption features in the thermal infrared. And with these molecules, we can characterize exoplanet atmospheres, and then we can calculate CO ratios, NO ratios. And these can help us distinguish between different models of planet formation. Such as core accretion, where the core forms first and then the atmosphere is accreted, or disk instability, where the disk fragments and coalesces into planets. Additionally, as you can see here for the Earth-like planets, the spectral energy distribution is made of 2 parts. The short wavelength part is reflected starlight, and the longer wavelength part is the thermal emission. And actually, in cooler planets, the thermal emission emits a lot more flux than in the near infrared. If you combine this with molecules like ozone, which also have absorption features in the thermal infrared and indicate biological processes, then you can see that this is a really good place to start looking for Earth-like planets in the habitable zone. However, that is a little bit futuristic at the moment, so I've mostly been looking for gas giants. But for gas giants, we can also tell a lot about the planet depending on their brightness in the mid-infrared. So as my basic planet, I've taken here a young gas phase only 10 Jupiter mass planet, fairly typical. And the flux changes depending on various properties. So if the planet ages and cools down, the flux reduces, as you can see on the left, to a few percent of what it was before. But this is still a lot better than in the near infrared. But if we have this young planet and we add dust or clouds to the atmosphere, then we see an increase of 20 to 30% in the flux of the planet. This means if we have a 5 or 10 sigma detection, we can actually distinguish between these different atmospheric models. And then finally, if the planet is still very young, it has a circumplanetary disk around it, and accretion might be going on. And these processes are also expected to be very bright in the mid-infrared. So then we get up to 100 times more flux. So for my research, what I've been doing is I've looked at mid-infrared data, specifically with VISIR and NEAR, and I started off with the HR8799 system, which you've already seen a few times this morning. It's fairly famous because it's the first directly imaged system with multiple planets. There's actually 4 companions that you can see here. So if we want to look at this in the mid-infrared, then the first thing we have to do is still to get rid of the starlight, because even with much better contrasts, the starlight still dominates the image. To do that, I ended up developing a new method for the PSF subtraction, which I call circularized PSF subtraction. And just to demonstrate, I've got a VISIR image here of a binary star, Alpha Cen. And you can see the dark spots from the chopping and nodding as well. So what we want is to get rid of the central star, Alpha Cen A, without getting rid of the companion. And to do that, we average over the full rotation of the image. So we azimuthally average over the real data. And then what we get is a circularly symmetric version of the PSF, where the central star can be subtracted, but because the companion is smeared out, we won't be subtracting too much light from the companion itself. If we do that for HR8799, we get the following map on the left here. And unfortunately, as you can see, we didn't have sensitive enough data to actually get a detection. But what we could do was create flux limits for any potential companions in this system. And if we take a closer look at one of these companions, in this case HR8799C, but the other ones are fairly similar, then we can use atmospheric models to try and figure out what kind of flux we would expect at these wavelengths for this target. And what we can see is that actually the expected flux is quite a lot less than the 0.8 milligensky limit that we get. I should mention this is still a factor of a few more sensitive than more traditional methods like ADI on this data set. So from this flux limit, we can also then compute with the near infrared data that we have a mass limit for this companion. And then for the system, we find a mass limit of 30 Jupiter masses. Considering the predicted mass of these planets is 7 to 8, that is all fairly consistent. But it does show us that we actually need more sensitive data. And fortunately, with NEAR, which was essentially the addition of adaptive optics to VISIR, there was the opportunity of the science verification. During this science verification from a number of different programs from different people, a total of 11 planetary systems were observed. 4 of these are older stars in the solar neighborhood. And for these systems, you can see that the mass limits that we've derived are actually down to a few Jupiter masses. And 6 of these systems were also much younger systems, Herbig AB stars with protoplanetary disks around them. And for these, we would expect the planets to still be forming. But for a number of these systems, we were able to exclude accreting planets with circumplanetary disks. So this actually reinforces what we just heard, that giant planets at large separations are rare. So even with NEAR, what we would ideally want is more sensitive data, which we will be able to get with METIS, hopefully. I've included a plot here of the sensitivities of a couple of different observatories. But what we can get with METIS is 10 times better sensitivity than NEAR, so that is 40 times better than VISIR, but also a 5 times better spatial resolution. And that bit is going to be very important if we're going to continue to look for planets, because if these planets at large separations are rare, then we need to get closer to the star, and for that we're going to need the better spatial resolution. With METIS, we will be able to observe 79 out of the 100 or so young previously imaged planetary mass objects in less than 2 hours. So that's really going to be a huge improvement. Additionally, with this new sensitivity and spatial resolution, Earth mass planets in the habitable zone actually become available. So just to summarize, we did N-band observations with both VISIR and NEAR. To do this, we developed a new method of PSF subtraction. And even though there were no detections, we were able to put some really stringent mass limits on 11 different planetary systems. And if we want to continue doing this in the future, then both the sensitivity and the spatial resolution of METIS on the ELT will be very important. Thank you.
Thank you very much. This was also a really nice talk. Let me check the Slack channel. No question yet. So I'll start with mine. I was wondering how long the observation of the HR 8799 system was, and whether those planets are in principle within the reach of VISIR NEAR without going to like 10 nights like you did for the AlphaSense system.
Yeah, so the HR 8799 data was in total about 10 hours of data. But to actually image these systems with VISIR in its current state would take closer to 100 hours. With NEAR, it would be possible in a similar amount of time, so 10, 20 hours. And then with METIS, it'll be, I think, less than 1 hour.
Let's go for that.